That is a summary. Okay, in chapter 5, we already said about second law of thermodynamics states that the processes occur in certain direction, not just any direction, and the process will not occur unless it satisfies both the first and second law of thermodynamics. And bodies can absorb and reject finite amounts of heat isothermally are called thermal energy reservoir or heat reservoir. So work can be converted to heat directly, but heat can be converted to work only by some devices called heat engine. Okay, other summary is for the thermal efficiency. The thermal efficiency of heat engine is defined as W net out or work net out divided by QH or high temperature. This is equals to 1 minus QL, Q of low temperature, divided by Q of high temperature, where W net is the net work output of the heat engine, QH is the amount of heat supplied to the engine, and QL is the amount of heat rejected by the engine. Okay, we also see about refrigerators and heat pumps, that devices that absorb heat from low temperature media and rejected it to a high temperature one. So the performance of refrigerators and heat pump is expressed in terms of coefficient of performance or the COP. And for refrigerator, the coefficient of performance is QL divided by W net, or the heat rejected divided by work net, and is equals to 1 divided by QH per QL minus 1. And for COP of heat pump, it is QH divided by work network input, and the WH we know as the heat rejected to higher temperature. Okay, so the COP of heat pump can be expressed by 1 divided by 1 minus Q rejected by per Q absorb or Q in. Okay, other than that, we also learn about Kelvin statement, that's saying that second law of thermodynamics, saying that no heat engine can produce a net work or net amount of work while exchanging heat with a single reservoir only. So if only have one reservoir, we cannot produce amount of heat. And the Clausius statement also said that of the second law state that no device can transfer heat from any cooler body to a warmer one without leaving an effect on the surroundings. So any device that violates the first and second law of thermodynamics is called perpetual motion machine, PMM. And I mentioned there's no PMM really works in the real world. And A process is said to be reversible if both the system and the surrounding can be restored to their original condition. It's important to original condition. Any other process is irreversible. And the effects such as friction, non-quasi-equilibrium, expansion or compression, and heat transfer through a finite temperature difference render a process irreversible and are called irreversibilities. And we also know about Carnot cycle. That is a reversible cycle that is composed of 4 reversible processes, 2 isothermal and 2 adiabatic processes. And from the Carnot principle state that thermal efficiencies for all reversible heat engine operating between 2 same reservoirs will be the same, and that no heat engine is more efficient than a reversible one operating between the same 2 reservoirs. This statement forms the basis for establishing a thermodynamic temperature scale related to heat transfer between reversible devices and the high and low temperature reservoirs. So this is where if you have a reversible, the QH per QL will be almost as temperature H TH per TL. Therefore, the QH and QL ratio can be replaced by temperature H, TH and TL ratio. This is only for reversible devices, where TH and TL are the absolute temperature for high and low temperature reservoirs respectively. Other than that, we know that heat engine that operates on a reversible Carnot cycle is called Carnot heat engine. And the thermal efficiency for Carnot heat engine as well as all other reversible engines is given by is given by 1 minus TL per TH. And this is maximum efficiency a heat engine can have while operating between 2 reservoirs at temperature TH and TL. This is the maximum. Okay, for the COPs of reversible refrigerators and reversible heat pumps are given with this equation, so you can use temperature equation. SOP for refrigerators is TL divided by TH minus TL, and for COP of heat pump, reversible heat pump, is TH divided by TH minus TL. Again, these are the highest COPs of a refrigerator or a pump or heat pump can have while operating between the temperature limits of TH and TL.